Chapter C, partial pressure. We're going to consider here a container with gas, and we'll make the container a simple cube, and the volume is V, and the temperature is T, and the pressure is going to be P. And the ideal gas law, the pressure times the volume, is equal to the number of moles times the ideal gas constant, which we use R star for, since we reserve R for something else, as you will see again in this class, times the temperature. Now we're going to consider a mixture of gases like air. Has nitrogen, has oxygen, argon. So in that case, we can write the number of moles as consisting of the number of moles for the oxygen, the number of moles for the nitrogen, plus dot, dot, dot. They all have the same temperature, they all have the same volume, and they don't interact with each other. So the pressure here can be listed as the pressure coming from the nitrogen and the other constituent parts, like that. Now, this is Dalton's law that involves partial pressure, and we can write the ideal gas law for each of the individual constituent component parts, and the total pressure is given by adding all the pressures. These are called partial pressures. And since the gas content is independent of the individual component parts, we can write the ideal gas law for each component part. But before I do that, let me just go ahead and work this out. P1 times V1 plus P2 times V2 equals, well, dot, 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 equals, and then here we'll have N1 plus N2, dot, 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 R star T. Now, since the gases are independent, we can write for the ith component, we'll write Pi. I can consider I to be 1, 2, 3, 4, or nitrogen, oxygen, argon. So Pi times V is equal to Ni times R star T, since the gases are independent. So now what we're going to do is divide by the mass of the ith gas. All right, so we do that. We'll have Pi, volume is the same for all the gases, divided by the mass of the ith component is equal to the number of moles, and we divide by the mass of that component, and then R star times T. Now we note two things here. First of all, we note that the mass of the ith component is equal to the number of moles of the ith component times the molar mass. This is the mass for 1 mole, and this is the number of moles, so that would get you your mass. Also, remember our definition from the earlier class. If you take the volume and divide by the mass, you get alpha, which is the volume per unit mass. And also notice that alpha, which is equal to the volume divided by the mass, that the density is the mass divided by the volume. So we have the nice relationship that alpha equals 1 over rho, the density, and the density is 1 over alpha. So what we can do there is we can look at this V over mi, which is the alpha I. We can replace that with 1 over rho I. So let's do that and rewrite this. So pi times the alpha I, but I'm going to write it as 1 over rho I, is equal to, on the right-hand side, I'm going to write the r star and t in the numerator, and I'm going to write the flip of this in the denominator, mi divided by ni. So now, when you divide by mi over ni, you flip it, and we'll have ni over mi. So we have this equation. All right, so this equation implies that the pressure of the ith component is equal to, bring the rho on the other side, rho I, and then I have r star over, and now notice, mi divided by ni, if I take mi and divide by ni, I get the big mi, I get the molar mass. And then I have the temperature. This is the practice in atmospheric science, and this combination here, where you have the r star over the mi, that is what meteorologists like to call r sub I. You can think of this as the ideal gas constant for the ith component. It varies dependent on the gas, since the molar mass is going to be different. So this becomes the equation, the pressure of the ith component is rho I times the gas constant, r sub I, which depends on the gas, times T. That's a nice equation. Now I want to consider the air, not in terms of nitrogen and oxygen. I just want to break down what's in here in two gases, dry air and water vapor. So that's going to be then dry air and water vapor. So then I have two constituents that are there. So using the Dalton's law, the partial pressures get added to get the total pressure. So here the total pressure is the pressure of the dry air plus the pressure of the vapor, and we like to use E for vapor. Now let's use this equation here twice. We have the pressure for the dry air is equal to the density of the dry air times the gas constant for the dry air times the temperature. We can also write this as the pressure of the vapor is equal to the density of the vapor times the gas constant for the vapor times T. Now we like to refer to this as E. So then we have here three equations for our course. We have this equation that gives the total pressure in terms of the dry air pressure and the vapor pressure. That's our equation 7. This equation, which is the ideal gas law for the dry air, is our equation 8. And this equation that says the vapor pressure E is equal to the density of the vapor times the gas constant for the vapor times the temperature, this is our equation 9. Now we are essentially finished with this chapter, but I want to do two more things. And that is, I like to express the molar mass of dry air in terms of the molar mass of nitrogen, molar mass of oxygen, and molar mass of argon. And I'd like to express the molar mass of vapor in terms of its constituents. So to do that, we start out with the mass of the gas consists of the sum of the constituent parts, m sub I. That gets you your total mass. Now, your total mass is also equal to n, number of moles, total number of moles, times the molar mass. Since the molar mass is the mass per mole, you multiply the number of moles, you get the mass. So this is going to be equal to, and I apply the same principle here, that this mass sub I is the number of moles for that ith component of the gas times the molar mass of that constituent part of the gas. So we're basically using the n big M formula for the little m, and the same thing here, the little nm big M formula with the i's for the mi. Now I want to divide by the total number of moles, and then I'll get the molar mass for the combination, the gas that's in there, is equal to the sum of the number of moles divided by, that's the number of moles for the ith component, divided by the total number of moles times mi. And what we do here is we refer to the number of moles for the ith component over the total number of moles as the mole fraction for that component of the gas. Say Ni is the moles for nitrogen, you divide by the total number of moles of the air, and you would get the mole fraction for nitrogen. And this then is written as the sum Yi Mi. Now this is not surprising. We could have written that down at the start, because if you want to take some kind of average, this is what you do. Like say, suppose I have a 60 and another 60, and then I studied hard and I got, say, 380s in my 5 test. Then to find the average, you would divide these exams by 5. But notice that 2 of the exams are the same, so you could say 2/5 for the 60 and 3 of the 80s divided by 5. So there's 2 60s here, 2 times 60, and then you have 3 80s, 3 times 80, and you're dividing by 5. So this is like Ry. It's saying we have 2 of this type, and we then multiply 2/5 is your fraction, your mole fraction. This would be like your fraction for that, for the 60, for the 60s, the score of 60. That would be the fraction. So this is a very, very common formula that we would use intuitively if we were like taking averages of exams and things. So we're about ready now to do the molar mass for the dry air. We're going to need here a little table. So we'll have here the gas, we'll list. We'll need Yi, we'll need big Mi, and then we'll need Yi big Mi, and then we'll need to add that column up. So let's start out here with the first gas, say nitrogen. Now nitrogen consists of 2 nitrogen atoms. It's a diatomic molecule. And the mole fraction is, well, the atmosphere is 78% nitrogen, so the mole fraction would be 0.78. Then we have oxygen, 21%, so that would be 0.21. And then argon comes in at 1%, which would be 0.01 for the mole fraction. Now there are other things in air, trace elements, but this is pretty much it. See, this adds up to 100%. 78%, 21%, that's 99%, and 1% gets you 100%. So this is a very, very good approximation. Now we come to the molar masses. Like, what's the molar mass for nitrogen? Well, here's where we need to go have some chemistry. So the nitrogen atom has 7 protons and has 14 protons plus neutrons when you add everything together. So you can think of this as 7 protons and 7 neutrons. And this is the total number in the nucleus, which we call nucleons. We could say 14 nucleons. This is the common form of nitrogen. But when we do this analysis more carefully, they'll actually go to the periodic table, and this 14 will be something like 14 point something because they're taking a weighted average of the different isotopes, but mostly it's nitrogen 14. And that's why I sometimes call that the atomic weight, because to do a weighted average there. And the key idea is that that 14 refers to how many grams you need to have 1 mole. So that's important to remember. Then we have, for the oxygen, we have 16 nucleons and 8 are protons. And then for the argon, we have 40 nucleons and we have 18 of those are protons. So what we want to do next is figure out the molar mass. And for the molar mass of the nitrogen, we're going to have 2 of the nitrogen atoms, so that'll be a 28. So this is 28, all right? Then for the oxygen, we're going to have here 2 times 16, so we'll have a 32. I'm going to be a little cavalier with the significant figures at this point, but when more careful analysis is done, you're going to get the answer I'm going to get here. So here you have 40 is for the argon. So now we multiply through 0.78 times the 28, and that gives us 21.84. Once again, being a little cavalier with significant figures, having a little extra there. That may, strictly speaking, you shouldn't do that. If you start out with 2 significant figures, you should not start adding significant figures. But this works out. This works out well if you do a more detailed analysis. And then 0.21. So you can see these numbers making sense. This is close to 3/4, and 3/4 of the 28 is going to be 3 times 7, 21. And this is like a fifth. A fifth of 30 is 6. This would be close to 6, 6.72. And this is 1/100th of here. So you move the decimal point, boom, boom, over twice. And that's going to give us a 0.4. So now we need to add these up. And if we add these up, we'll get over here a 6. And here we'll have 11, and 8 is a 9. Carrying 1, and that's 22, and 6 is a 28. And to emphasize what we have here, this is grams per mole. So that's the molar mass. Okay, what about for vapor? Well, vapor actually is easier because you have H2O and hydrogen, common isotope. Isotope means the same number of protons, but different number of neutrons. So the isotope that's common for hydrogen is just 1 proton and no neutrons. So there's a 1 up there. So for H2O, you need 2 of these. That's 2 plus an oxygen. That's 16. So 2 plus 16 is 18. So therefore, the molar mass of vapor is 18. I'll throw in a 0.0 there. more careful analysis justifies what I'm doing. And then a real neat thing to see here is a ratio, which is common in atmospheric science, to look at the ratio. Epsilon is the molar mass of the vapor divided by the molar mass of the dry air. And that's going to be 18 over 28.96. And if you do that on a calculator, you get 0.622. And this value holds up if you are more careful with your analysis and look up in the periodic table what's not exactly 14 or 16 because the isotopes are weighted in, the atomic weights, you still get this. Now, notice that earlier in our course, we did look at the ratio defined in terms of the gas constant. So I want to show you that this is consistent. If we have our formula that the gas constant here is equal to R star over M, let's say we have that for the dry air, then MD for the dry air is R star over RD. See, it's inversely proportional. So what we're saying here is that the molar mass is inversely proportional to the gas constant. So therefore, what we got earlier in our course is consistent with this, because since that inverse relation occurs, you would put RD in the numerator and RV in the denominator to get that 0.622. One last thing I'd like to do for you here is something that I think is important to have in the back of your mind to understand, and that is that we can relate the microscopic properties of a gas, its say mass of a particle, and we'll use n sub naught or n sub 0 because we use an m a lot of times. So here if we have, go head back to our little box here, and in this box, let's say we have a gas, and all the gas particles are the same, and they have mass m naught, and in there, they're all moving, say, with velocity v. Now, this is velocity v, and I'm going to make them move either left or right, up and down, or in and out. That's not the case. This is a super simple model. So we have here 3 dimensions, which I could list like this. The x is left and right, y is in and out, and z is vertical. But this is a very powerful derivation here. Area A everywhere, and say length L, it's a cube, right? And L. And the velocity of the particles would be, well, if one started at the far right here, and it's going velocity v, it would go across here, L, in time t. So let's go ahead and let that time t be the time it goes from the far right to the left. Now in that time t, all the particles that are in that region to the left of that edge, they're all going to hit that wall once over here. And they're going to cause a pressure. So we have n particles where n over 3 go in each of the directions, super ideal model, which is of course not true in reality, but we're going to get a very important result. That means that the particles that are moving to the left would be half of n over 3. That'd be n over 6 moving to the left. Now when the particle hits that wall, it's going to change its velocity and bounce back and go the other way. So now I'm going to use Newton's law, F equals ma, to calculate the force. Well, we have the mass, m naught, and the acceleration is the change in the velocity divided by t, the time. So here the velocity is initially going to the left. We'll call that's the minus v, since the plus x is to the right. And then after the bounce, it's going plus v. So for the delta v, you want the final minus the initial. Well, the final is the plus v, and the initial is the minus v. So the change is 2v. So the total force would be, remember we have n over 6 particles. We're all going to hit that wall once in this time frame, t, and all going to experience that delta v. So therefore, we can write down n over 6 times m naught 2v is your delta v over t. Now we can introduce the pressure. Pressure is equal to the force per unit area. And here we have the area A involved, the relevant area for the reflections and the bounce. So that means we can write down the pressure times A, which would be the force, and then write this down again. N over 6 m naught 2v over t. Now I would like to multiply by the length L, because that would give me area times L is the volume. You can see we're heading toward the ideal gas law here. So we multiply by L. Let's see, this is going to be 1/6 of 2, so that's going to be n over 3, and have m naught. And we'll have a v, but remember we're multiplying by L, so we'll have an L over T. So we just check L times PA, and then L in here is going to be m naught v L over T, and then 2 over 6 is 1/3. Notice that if the L coordinate it with that T, take that ratio, that's going to be that's your velocity. So this is the velocity that we had earlier, and this is the volume. So we're looking like the ideal gas law here. This is very insightful. So this is equal to here n over 3, and this is going to be m naught and v squared. Now remember from physics, the kinetic energy is 1/2 mv squared. So that means PV equals, if I put a 2 here, I can then have a 1/2, cancels. So here, the 1/2 cancels the 2, and this is the kinetic energy. That's the kinetic energy of a gas particle, but PV has to equal the number of particles, KT, where that's the Boltzmann constant. Wow. Now also PV, you can think of it in terms of moles, and then the ideal gas constant from chemistry times T. And in our course, from time to time, we remind everyone that N R star, when that's the number of moles, is equal to the number of particles times the Boltzmann constant. You have a different constant depending if you want to think of moles or number of particles. So here, let's write down 1/2 m naught v squared, the kinetic energy. And let's note that the n's cancel, and if I bring this over to the other side, I would have 3/2. This is a very important result in physics, that the kinetic energy of the gas particle is equal to 3/2 kT. We have a correlation between temperature and the kinetic energy. So the temperature is given by the mass of the particle times its velocity squared. But suppose that we make our model a little bit more, let's say, realistic. And let's say that the particles travel at different velocities. So if we come over to here, we would write down PV, pressure times the volume. And here we're going to have, say, N1 particles are traveling at V1 speed, and then 2 particles V2 speed. So that would mean we would have here N1 particles traveling at the V1 speed, plus N2 particles at the V2 speed, dot, 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 and we would have here M0 over 3. So that would be a generalization to a more realistic situation. Now what I would like to do is multiply by n, big N, and divide by big N. So this becomes N1 over N V1 squared plus N2 over N V2 squared. And then I have my M naught over 3. Now this is exactly what we've been doing over here with this weighted average. See, this is the fractional number that are going at velocity 1 and the fractional number at velocity 2. It's just like taking the exam scores. So we're getting the average of this V squared. So this is going to be N times V squared average. That's what this is like the exam scores. And then we'll have an M naught over 3 hanging around. So we have the same equation we had above. The only difference is we had to put a bar over the V. So we're going to do that here. 1/2 M naught V squared bar is equal to 3/2 KT. Now, this equation is very important. We can see that it's the same formula we had here, but now we're looking at the average velocity squared. You're squaring the velocity. And this would be the average kinetic energy per particle. Now what's even more fascinating, and it's why I'm doing this, is that if you're looking at angles where they're bouncing off the floor or they're bouncing off the wall, you get the same answer. So this helps us gain an incredible amount of insight into the microscopic and the macroscopic. This is microscopic stuff over here, the mass of the individual gas particle, the average velocity squared of the gas particle, and that translates to 3/2 KT, and that's a temperature. So temperature, macroscopic, comes from the kinetic energy, average kinetic energy of the gas particles. Now in the old days, when they found this to be true, this equation, they then said, well, suppose you have velocity to 0. Well, then you have absolute 0. So they said that all motion stops if you're super cold like that. But we know since quantum mechanics that motion doesn't stop, but you have the lowest energy state. So you can think of some jiggling, some motion there, but it is the lowest possible energy state in quantum mechanics. All right, that concludes chapter C. And with these additions, this makes this chapter a very rich chapter.